Hey folks, in this lecture we're going to be talking about how we go about comparing a sample of data to a population. We'll talk about some use cases for that, and we'll talk about some specific tests that we can use. The specific tests that we'll talk about are the one sample z-test, the one sample t-test, and the Wilcoxon Signed Rank test. The one sample z-test has a couple assumptions that need to be met in order for the results to be valid. First, we need to be dealing with a random sample of data. That means that any value within the population has an equal likelihood of being chosen relative to any other value. The data need to be measured at a continuous level, so that means that they would need to be interval or ratio level. Our observations need to be independent, meaning that the selection of one observation doesn't change the probability of another subsequent observation being selected. And also, and this is critical for the z-test, we have to know the population variance. This is a rare occurrence. It is not likely that we're going to know the population variance, but if we happen to know what the population variance is, then we can possibly run a one sample z-test. The last thing that we will need is for the data to be distributed roughly normally. And you can either have data that are distributed normally, or if the sample is large enough, thanks to the central limit theorem, the effects of non-normality are drastically reduced. So if we're going to conduct a one sample z-test, well, when do we conduct that test? Well, we want to use it, of course, if the assumptions are not violated. So those assumptions need to be met. And we want to make sure that we're trying to compare one sample to a population. The test actually compares the mean of the sample to the mean of the population. And it does so with the formula I'll show you next. The one sample z-test very much follows the structure of the formula that I gave you in the last video. To calculate our z statistic, we will look at the difference between our sample mean and the mean of the population, and then we'll divide that by the population standard error. That is the population standard deviation divided by the square root of the sample size. Okay, so I'm just going to do this in a language that I'm comfortable in. You can do this in Excel, you can do this by hand. As long as the numbers aren't too big, this should be just fine. If you don't choose to use the example of how to enter syntax into SPSS. So just as a reminder, Z is the difference between the sample mean and the population mean divided by the population standard error. So if we have the sample, then we can calculate a mean from that. If we have the population mean and the population standard deviation, and assuming that our data are sufficiently normal, randomly selected, and independent, we can go ahead and calculate our z statistic. And so that's all this function is doing. It is doing exactly what is in this here. It's figuring out what n is, what the sample mean is, and what the sample standard error is, and then it divides the difference between the sample mean and the population mean by the standard error, and it gives us back the result. And so if we give it a sample where we have values 1, 2, 4, 5, and 10, and we tell it that the population mean is 4, and the population standard deviation is 1, the z that it calculates is 0.894. So we can take that value and we can go to a z-table. This is a negative z-table. I'll just back up so you see what it looks like. So it's telling me the proportion under this curve here to the left of z. And so you see all the z values are negative. So we're going to go down the column here and we're going to look for our 0.8, and then we're going to go across until we get to 0.09. So our our z is associated with a probability of 0.18673. So about a little over 18% of the values in this population are going to be more extreme than this. And if we had an alpha of 0.05, this would not be enough to reject our null hypothesis. And so we have to accept the null hypothesis that these data do not come from a different population than our reference population. But as you can see from this formula, changing the standard error, increasing the sample size or decreasing the standard deviation of the population would give us a larger z. So why don't we do that? Let's go ahead and first let's just be more sure of the mean of the population. We're going to decrease our standard deviation. Let's say our standard deviation for the population was 0.5 instead of 1. If we were to run this again, now we see that we get a z value, a z statistic of 1.78. And if we go back to our same table, and we go down the side and we look for 1.7, and then we go all the way across to look for 8, then we see that there are 0.3754. That's the proportion of values that are more extreme than this. So a little under 4% of the values are more extreme than this value. And so if we had this and an alpha of 0.05, we would reject our null hypothesis, and we would accept our research hypothesis that these values come from a population that is different than our reference population. Specifically, since we're using this one-tailed z-table, we're talking about these values coming from a population smaller than the population that we referenced. If you're using a negative z-table or a positive z-table, but you want to do a two-tailed test, we take advantage of the fact that the z distribution is normal and perfectly symmetrical, and we would just divide this p-value in half. So we would divide 0.374 in half, and we would know that a little over 1.5% of the data would be on either side of that distribution. Now let's talk about a one-sample t-test. Remember, the t-test is an approximation for the z-test once our values get, our number of observations get large. Once n is very large, z pretty much approximates t. It also has similar assumptions. We need our data to be randomly sampled. Our observations need to be independent, and we need to be dealing with interval or ratio level data. But we also need to avoid outliers. Right? So we don't want to have any outliers in our data. That's one thing that was a little different than with the z-test. And we want to use this t-test, of course, when the assumptions have not been violated, so when the assumptions are upheld, and when we're comparing one sample to a population, but the population variance is unknown. If we don't know what the population variance is, the best that we can do is to use a t-test, which will compare the mean of the sample to the mean of the population, but it will weight that difference by the standard error of the sample. And so let me show you the formula. So the formula for the t-test, again, is similar to that of the z-test. We're still looking at a difference. In the case of the one sample t-test, we're looking at a difference between the sample mean and the population mean. The only difference is that we're dividing by the standard error of the sample. And so we take the sample standard deviation and divide by the square root of the sample size. The only thing that is different in this formula is that we're using S instead of sigma, or the sample standard deviation instead of the population standard deviation to calculate our standard error. So we can use SPSS directly from this graphical user interface here to calculate a one sample t-test. You'll go to Analyze, down to Compare Means and Proportions, and then we'll select the one sample t-test. You'll have a little screen that pops up that looks like this, and it will ask you which variable you're going to use for your one sample t-test. Let's not use screen time. Let's see what else we have. Let's use YouTube likes. Okay. Now, the question is, or rather the thing you need to remember is to change this box down here. When you first open this up, it will look like this. It will have a test value of 0. Test value in this case means what is your population mean? So we're going to enter the population mean into this, our reference mean here for comparison. I'm going to go with 1200. Sorry, 12,000. Now, you can either check or uncheck estimate effect sizes. There's no reason not to have that checked. Remember that the effect size is probably the closest thing in statistical terms to what we mean in common language when we say that something's significant. So it's always a good idea to take a look at your effect sizes. Once you've selected that test value, there are some other options that you can include. And the one that I want you to pay attention to here is the confidence interval percentage. Confidence intervals are the range of values over which, in the case of a t-test, over which we think the true mean of the sample's population lies, right? So you can also estimate the confidence interval. I'll leave that at 95%, which will match our alpha. And then I will hit OK. And then your output screen will look something like this. Right, so you'll have the variable, the number of values, which is 142, the mean of those values, which is 14,645, the standard deviation, which is 10,511, and the standard error of the mean, which is 882.1416. And then when you look at the one sample t-test, it will give you your t-statistic of 2.99. Oops. Sorry. Double clicked on that, it opens something else. It'll give you your degrees of freedom, which is 144, one less than your n. And then it will give you both your one-sided and your two-sided p-values, as well as the mean difference. And if you selected the confidence interval, it will give you the confidence interval. Now, before we talk about effect sizes, I want to talk about the significance here. It is important for you, ethically important for you, as in this is the standard of what is to be done in statistics. You should decide the nature of your test before you calculate your statistic and your associated p-values or critical values. So you need to decide whether you have a one-sided test or a two-sided, one-tailed or two-tailed test, and that is going to be based on your hypothesis. All right, so depending on which one you decided beforehand, you will only pay attention to that significance value. Don't pay attention to the two-sided value. If you selected one-sided, don't pay attention to the one-sided value if you selected two-sided. And now here you see there are two estimations for effect size. There's Cohen's d, and then there's Cohen's d with the Hedges correction. So the effect size here is still about 10,500 and some odd likes. Okay, so what do we do if you can't calculate your if you can't calculate a t statistic or a z statistic? What if the assumptions of those tests are violated too much? Well, if we can't fix the data, we can fix the test that we use. And in this case, we could use a one sample Wilcoxon Signed Rank test. So this is a non-parametric test. It doesn't really care too much about the distribution of the data. It doesn't have many assumptions about the distribution of the data, but it does still have some assumptions. And those assumptions are that the data are at least ordinal. So you cannot use categorical data for a one sample Wilcoxon Signed Rank test. You need to have at least ordinal data, but you could do this for interval or ratio level data as well. Those observations need to be random and independent, just like in the one sample t-test and one sample z-test. And with respect to the distribution of the data, the only thing we really need is that the population is symmetrical around the median. So you could have a bimodal population, you could have a multimodal population, but as long as it is relatively symmetrical around the mean. So the right half sort of looks like the left half if you split it at the median, sorry, not mean. As long as it's symmetrical around that median, our assumptions are supported, and we can use this one sample Wilcoxon Signed Rank test. So you only really want to use this when the assumptions of the T and Z test are violated. If we're thinking about normality, your data have to be really non-normal before we're going to use this one sample Wilcoxon Signed Rank test. Remember that T test is pretty robust against violations of normality. So if it's only a little non-normal, right, your data are slightly skewed to one side, then if it's only a little non-normal, then go ahead and use the T-test. But if it's drastically non-normal, then we can use the one sample Wilcoxon Signed Rank test. So you were still comparing one group, a sample group, to our reference population, but we're not comparing the means anymore. Now we're comparing the data in that sample to the median of the population. And remember, medians are far less susceptible to things like outliers. So if you have outliers in your data and you couldn't use your t-test, that's the part of the reason that we can't use the t-test is because the outliers have an outsized effect on the mean. But those outliers are virtually ignored by the median. So the Wilcoxon Signed Rank test still makes sense. All right, so we're going to compare those observations in the sample to the median of the population. And we're going to generate a table that looks sort of like this. You notice that I didn't give you a formula to calculate the one sample Wilcoxon Signed Rank test. So there's more of a process than there's a formula. Let me explain that process, and we're going to reference that table that you're seeing there on the left of the screen. In the first column, you have the raw scores. So these are the values that you collected, that you observed, right? They could have been the number of times that an individual called out sick from work. They could have been the heart rates of individuals, right? Whatever they are, as long as they're at least ordinal, we can do this, right? So we take those raw observations, and then we look at those raw observations, and anyone that is greater than the mean gets a score or gets a sign of a positive sign, so just a positive 1. Anything that's less than the mean gets a negative sign, or -1. Then we take the difference between each observation and the mean, right? So the difference between our mean, I'm sorry, I keep saying mean, but I meant to say median. The difference between our median of 4 and our score of 1 is -3, right? So we'll do those differences between the median and each score, and then we'll take the absolute value of those. So anything that's negative becomes positive, and then the positive ones stay the same. Now, any one of these that has a rank or a value of 0, so it's exactly at the median, we're going to ignore that in this next step. So we're going to take those out, and then everything that's left, the difference between the value and the median, the absolute difference between the value and the median, we're going to rank those. And so the smallest values will get the smallest rank. The largest values will get the largest ranks. But it's important to remember, we're not talking about the raw scores here. We're talking about the absolute value of the difference between each observation and the median of the population, okay? So once we're looking at that, you can see here that those individuals' observations that were only 1 away from the median, they're going to get the lowest ranks. Those that were 3 away from the median are going to get the largest ranks. Now, those rank numbers that you're seeing may not make sense, so let me clarify. When you have values that are tied, so we can see our raw score of 3 and 5, they are each only 1 away from the mean, and so they all have an absolute value difference from the mean of 1. So they would occupy the first, second, third, and fourth positions because they're 4 values. So what we do is we take those ranks and we take the average of them. And if you take the average of 1, 2, 3, and 4, you'll get 2.5, right? So every one of those ones has a rank of 2.5. And then the next value up would be 2, right? And so we have 1, 2, 3 2s, right? So we've already done ranks 1 through 4. So these 3 2s will get ranks 5, 6, and 7, right? And so we take 5, 6, and 7, and we average that. That gives us 6. So each one of those gets a rank of 6. And so our last value, that is 3 away from the median, well, that only has one value, so it doesn't have to split it. But we've already used 1 through 7, so this one gets a rank of 8. All right? Now we take that rank, and we're going to apply the sign for the value to that rank. So remember, those that were lower than the median get a negative sign. So all of our values that have that negative sign will now have a negative rank. So it'll be negative, but the same quantity as the rank. So our raw score of 1, which was below the mean by 3 points and got a rank of 8, will have a signed rank of negative 8. All right? And so we have all of our ranks here. Now, we're going to create two statistics. One is called T plus, the other is T minus. T plus takes all the positive scores, all the positive signed ranks, sorry, and adds them up. So in this case, we'll add up 2.5, 2.5, 2.5, and 6, and that should put us at 13.5. T minus takes all the negative ranks and adds them up, or rather, their absolute values. So it will take the 8, the 6, and the 2.5, add them together, and that should put us at 22.5. Now, you're going to take the lowest of those values, and that is going to be your comparison statistic. That is going to be the one that we calculate, and then we take a look at a table, right? Now, this one is different from the t-test and the z-test. With t-test and z-test, if our value, our critical value, is greater than, if our calculated value is greater than our critical value, then we reject our null hypothesis. With the Wilcoxon Signed Rank test, if the value that we calculate is lower than the critical value, then we reject our null hypothesis, okay? All right, now if you're doing this in SPSS or some other statistical package or program, you'll get a statistic, your T plus or T minus, and it'll give you a p-value. You always interpret the p-value the same way. If your p-value is less than your alpha, you reject the null hypothesis. Otherwise, or less than or equal to your p-value or alpha value, you reject the null hypothesis. Otherwise, you accept the null hypothesis and reject the alternative. All right, so what we're going to do is we're going to take our 13.5, which is our smallest value, and we're going to go ahead and we're going to take a look at a table that contains that value. So I gave you the link for this table in this week's list of items. This is a nice little website. You can choose one-tailed or two-tailed tests from here for your Wilcoxon Signed Rank test, and it gives you your critical values. Now, the things that you need to pay attention to are what your alpha level is, and since I'm going to be boring, I'm just going to stick with an alpha level of 0.05, right? And then you're going to look at what your n is. So what was the size of your sample? All right, and if we scroll down and we find our n value, right, which I think we had, yes, we have 9 values. So I'm going to scroll down to 9, and then I'm going to look over at the alpha of 0.05 or whatever your alpha was. And I look at this, and this is my critical value of 10. So I'm going to take that critical value, and I'm going to compare it to what we calculated, which was our 13 point something. Now, that value is larger than this critical value, and so we will accept our null hypothesis and reject our research hypothesis, right? Remember, we are dealing with the Wilcoxon Signed Rank test, and we do the reverse of what we would do with the t-test when we compare critical values. Now you can also calculate a one sampled Wilcoxon um, signed rank test in SPSS. We'll simply go to Analyze, and then instead of going to compare means and proportions, because we're not comparing means with the Wilcoxon signed rank test, we're comparing medians, right? And it is a non-parametric test. So we're going to go down to our non-parametric tests. We will click one sample since we're dealing with a sample that we're comparing to a population. And now this one is a little different. The default when you enter this is going to be that everything is on the right side, okay? What you're going to do is kind of the opposite of what you might think. You're actually going to remove things from here, right? And it kind of makes sense when you look at the headers. This is the test fields, right? So these are the things that are going to be tested, right? So I'm removing everything that I don't want to test, and I'm just going to leave the thing I want to test. Let's see what we're going to do. I think we did YouTube likes before, so why don't we do YouTube views this time, right? Okay, and so we have our objective set here. We can choose which test we're going to use, and we're going to keep selected the Wilson signed rank test. And now you need to give it a hypothesized median, okay? So just like you had to use the test value for the one sample T to give it your population median, here you're going to give it your population mean, sorry. Here you're going to give it a value for your population median, right? And so that is whatever you have had for that theoretical median or that theoretical population. I don't have a particular value, but I'm just going to kind of take a quick look here and say, let's go with 30,000. All right. This does not mean anything here. This is not a real test. That number is entirely just made up off the top of my head. So it was somewhere kind of in the middle of whatever values I saw. All right. I don't know. I have not looked at all 142 values here, so I don't know if this is the actual median for this sample or not. So you can think of this as us testing my guess, right? So once I've selected the test, and again, I have the field that I want to examine, I can click Run. And we'll just pay attention to what's down here, right, on our non-parametric tests, because this is what we just ran. It'll give us our null hypothesis that the median YouTube views is 30,000. It'll remind us what test we ran, the one sample Wilcoxon signed rank test, and it'll let us know our significance level and what we should do, right? So given our data, it's suggesting that we should reject our null hypothesis, right? When we take a look at this data, we have 142 values. The test statistic that we calculated was 10,122, right? It doesn't tell you whether this was T plus or T minus, and that's not particularly important. The standard error is 491. And then it gives us, again, our two-sided test statistic and what our p-value was. It is less than 0.001, all right? Here, our hypothetical median is 30,000, and the observed median is 249,747. So I was way off, right? One of the other really nice things about this is that it provides for you a histogram of the values in your sample. Remember, we need this to be somewhat symmetrical, right? This is somewhat symmetrical. It's not perfectly symmetrical, but kind of sort of okay,